Hi, good morning, everyone. Welcome to this new webinar series. So my name is Judy Zhang. I'm a professor in the Department of Civil and Environmental Engineering at Case Western Reserve University. So my research mainly focuses on water treatment. We're looking at the drinking water treatment, wastewater treatment, and we also look at the chemical safety. So there are many different chemical products, ranging from pesticides, pharmaceutical compounds to home care products. And we certainly look at how safe they are to the environment as existing chemicals and also new chemicals to be released. So today I'm going to take this opportunity to introduce to you a few very common techniques we're going to see in research and also in real water treatment. For that, I'm going to turn to my PhD student, Kai, who is in his third year. His research, I let him introduce himself. Hi, go ahead, Kai.
Okay.
So if you have any questions, feel free to use the chat function on the bottom of your screen and just type your questions into chat. We'll be happy to address all your questions by the end of our presentation. And also, if we run out of time or you have later questions after we finish, we have this email addresses on the screen. The first one is for Kai. My email is hjz13. Just feel free to email either one of us or both of us for follow-up questions. Okay, Kai, go take over then.
Okay, thank you, Professor Zhang. Okay, welcome to eWeek 2021. My name is Kai Zhang, and I'm a third-year PhD student. My research focuses on develop adsorption method to remove contaminants from water. And in the following slides, there will be one page about my research. Okay, let's go to today's eWeek. So here is the main content. Before we start talk about the technology used to treat water, we will look at a challenge. The challenge is to count 1 million rice grain. And then we will talk about 3 process used to treat water. Okay, let's start our challenge. Can you count 1 million rice grain in a short time? You guys may try to think about this short challenge. So here is a challenge. Try to quickly count 1 million rice grain. You may have your answer, but we can have a very short calculation to see if you diligently count those rice grain one by one, how long it will take. We have 1 million numbers, and assume you can count 3 numbers per second, and the total time will be 93 hours, or around 4 days, which means in the 4-day challenge, you cannot eat, drink, rest, or sleep. It's a really hard task, right? And you may think about, what about building a counting machine? It definitely works, but its cost will be very high, right? And you may think about hiring a lot of people to do this. It is still not cost effective. And in the environmental research, we have a simple way to finish this task. We can try to build a relationship between the weight of rice and the number of rice. It's quite simple. For example, in the first step, you can count 10 rice grain. It only takes 3 minutes, 3 seconds, right? And then you can use a balance to measure the weight of the 10 rice grain. And the second step, you can count 100 rice grain and then measure the weight. The third step, you can move to 1,000 rice grain and measure the weight. So in this plane, we have 3 points. We can draw a line which describe the relationship between the weight and the numbers. After we got this line, we can along the number axis and move rightward until we got the number 1 million and find the point on this line, and we can calculate the weight. After you finish this, you successfully convert this challenge of counting numbers to a simple measuring weight. Did this solution is what you thought in your mind? Okay, so after we finish this challenge, you may think or ask why we start this challenge. What's the relationship between this challenge and the topic today, water? Definitely, there's some relation between those two, and we can ask this question, ask the challenge once more, but in a different manner. So I will ask, can you count 6 multiplied by 10 to the power of 23 water molecules? It's quite similar, right? It's impossible for you to count so many water molecules, but you can measure the weight, right? You can try to measure around 18 gram water, and it's guaranteed. You will get around 6 multiplied by 10 to the power of 23 water molecules. Okay, after we answer this question, we can find another important point by compare those two numbers, 18 versus 6 multiplied by 10 to the power of 23. There are so many water molecules, but their total weight is only 18 gram. We can find water is so small, right? But from the biology class, we have already known almost half of the weight in our body is water. And the water is crucial and very important for ourselves. Every day we need to drink water, we need to use water to cook food, to do various things. So it becomes crucial to provide enough clean water. But in reality, the mission of providing enough clean water cannot always be achieved, and the water crisis is everywhere. There are some regions, they have a serious water crisis, and the only water they can get is some colored, heavy polluted water like this, and they're turning to you for help. Assuming you are a environment engineer or water treatment engineer, what would you do to help them when you got this heavily polluted water? You may try to find have some ideas in your mind. For example, if I was the engineer, I may think about distillation. It definitely works, and you can. But the problem for this method is that you need a lot of energy to do this, and it's quite slow. And now the people in that region are dying. They need a lot of water, a lot of clean water. So I may have the second way. filtration. It can work especially for the solids, but it may not be sufficient to remove the color. So what an environmental engineer will choose to do? Let's see their answer. And the first one, they would try to do physical treatments. And here we have the simulated colored water. And we have some materials to treat this water. The only thing we need to do is add the solids into the water and shake and wait for a few minutes. So now it's 10 times the speed. So you can see the blue color is almost gone, right? And for this method, we generally refer it as adsorption, and that's exactly the topic my research focused on. And the environmental engineer also had the second solution, a chemical-based method. Let's see how it works. So we still have the same simulated colored water, and it's also very simple. We just need to add a few drops of the first solution. And then a few drops of the second solution. And remember to shake, and the blue color is gone. Okay, so now we have two solutions to remove the color in the water. But in that slides, we noticed that there is not only color, but also some solids or some dirts in this heavily polluted water. So how to deal with the solids in the polluted water? And the environmental engineer also provide a solution. It's called coagulation. So we know the solids, we cannot wait, and filtration works, and we can use coagulation to remove those solids. Okay, let's see how the coagulation works. And in the first part, we introduce some materials or suppliers. We have the acid, we have the sodium hydroxide, and we have the water that needed to be treated. Also some containers, transfer cup, glass beaker, and the graduated cylinder, and the disposable pipette. We have used that in the two method to remove colors, right? And we have an instrument to measure whether we indeed remove those solids. And the stirring machine, we have 6 pedals. Okay, so now we need to get a certain volume of untreated water. And in this one, we use some simulated untreated water. And in the beginning, we would like to measure some basic properties of this water. Especially, we want to know how many solids in this untreated water. And we measure the pH first. It's almost neutral, right? Now it starts to measure how many solids in this untreated water. Okay, we got the numbers for the untreated water, and we will compare it with the water treated by coagulation. So we can see, look at those samples, we can find a lot of solids in this water. And now we add some ferric chloride solution to do the coagulation. We add a different volume of ferric chloride solution. And we can notice that the first one, we didn't add any ferric chloride solution. We just use it as the blank or use it as a comparison. And gradually we can find that the water in the last 5 gradually becomes clear, especially in the upper part. And we needed to wait a few minutes to let the coagulation finish. Now it becomes much clearer, which means we successfully remove almost all of those solids. And now we wanted to measure whether and to determine whether we indeed remove those solids in the water. And we got the numbers. We know the initial number for this sample is around 27. And now we got less than 1, or around 1 or 2. Okay, after we finish this step, we remove the color and the solids in this untreated water. And the next question will be, can we say the water can be drinking safely? Oh no, I forgot one sentence. The coagulation we can not only use coagulation to treat water, we can also see the coagulation in the natural environment. For example, the Mississippi River Delta is formed by the coagulation of sands, sediments, soil brought by the Mississippi River, like this. Okay, we continue our topic about the water treatment. As we mentioned, we remove the color, the solids, and we can get this crystal clear water. And the next question will be, can we directly drink this water? You may think about this question. And I guess in the age of COVID-19, we paid a lot of attention to the virus, to the microorganisms. So when you have this crystal clear water, I guess we would like to know whether there are some microorganisms. And if there are some microorganisms, how to remove them or how to reduce the possible harmful effects of those microorganisms. And the environment engineer have the solution. And we can use the UV to disinfect the virus or the bacteria or various microorganisms. So let's see how it works.
Natural and man-made water sources such as rivers, lakes, dams, streams, and stormwater tanks may contain living microorganisms, bacteria, fungi, or non-living structures like viruses, which can be harmful for human health. Therefore, water and wastewater treatment plants in developed countries test and treat water before it is used for drinking, bathing, filling swimming pools, food preparation, or cooking. At the same time, however, 60% of all infant mortality worldwide is linked to infectious and parasitic diseases, most of them related to inadequate water disinfection in underdeveloped countries. Chemical disinfection approaches like chlorine dosing damage the cell membrane of microorganisms and then enter the cell to disrupt the respiration and DNA activity. Chlorine also kills most viruses, but it requires retention times of up to 30 minutes or more. In comparison, UV light provides rapid, effective inactivation of microorganisms through a physical process. When bacteria, viruses, and protozoa are exposed to the germicidal wavelengths of UV light, they are rendered incapable of reproducing and infecting. Ultraviolet UV light is emitted by our sun. However, it's invisible for the human eye. On the electromagnetic spectrum, it's positioned between X-rays and visible light, with wavelengths between 100 and 400 nanometers. This spectrum is categorized as germicidal, meaning it damages DNA and sterilizes surfaces with which it comes into contact. For humans, suntan and sunburn are familiar effects of exposure of the skin to UV light, along with an increased risk of skin cancer. When microorganisms or viruses are exposed to UV light, their nucleic acids are damaged in a way that they are rendered incapable of reproducing and infecting. Bacteria absorb light for growth process, therefore high-energy UV light is absorbed as well and enters cellular RNA and DNA. This absorption of UV energy forms new bonds between adjacent nucleotides, creating double bonds or dimers. The longer the exposure to UV light, the more the thymine dimers are formed in the DNA, and the greater the risk of an incorrect repair or missed dimer. If cellular processes are disrupted because of an incorrect repair or remaining damage, the cell cannot reproduce or infect anymore. It has been proven that UV light treatment is a rapid and effective way to inactivate a wide list of pathogenic bacteria and viruses. Unlike chemical disinfection like chlorine dousing, UV light also eliminates protozoan parasites, which cause, for example, malaria. However, UV disinfection is usually a single-pass treatment, and if used insufficiently, bacteria strains could regrow during transportation from treatment facilities to private households. Thanks for watching, and if you like our 3-minute tutorials, please subscribe and don't forget to give a thumbs up.
Okay, with those methods, we can partly solve the water crisis in some regions, but in our daily life, especially for the drinking water treatment, the process are much more complex, and there are a lot of process involved for the running water or the tap water treatment, and you need to pay much more attention to that. And lastly, here are some keywords about today's sharing. If you are interested in some contents in these slides, you can use these keywords to find more information about the sharing today from the internet. Okay, thank you.
Thank you, Kai. That's very interesting. So you have learned some very basic concepts we use very often in water treatment. So we have talked about the calibration curve that's going to help you quantifying a very large or very small quantity. You have learned some oxidation to remove contaminants, certainly physical adsorption, and you have seen a video on how we do coagulation tests to remove solids, and finally using UV to disinfect microorganisms in contaminated water. Any questions? Please feel free to type your questions into chat. And Kai, could you go back to your first slide?
Okay.
I just want to bring up our email addresses again, just in case you have follow-up questions you want to ask later on. And I do know this video should be available. So and if you want to watch it again or have a specific question for any of these, contact us. We'll be happy to work with you. If no more questions, thank you very much. It's very good for you to participate in eWeek, and we look forward to seeing you in the near future. Bye-bye, everyone. Have a great week.